here, let's start. This is the motivation for how this is going to go. There's two parts to this. It's going to be line integrals for scalar value functions, and then we're going to apply this to what we've been talking about in fields. So remember from all the way at the beginning, we started doing these curves that were parameterized, and these are suddenly important again. So x of t and y of t, we can do this in 2 dimensions at first, and then we always have a specify a to b interval for the parameter. And so what's going on here is if I draw here's x, y, and I have a curve that starts somewhere, ends somewhere. This is parameterized in R2. So the very first place that it starts is the coordinate of x of t naught, and y of t naught. And then it's going to progress and it's going to conclude all the way up at the top with x of tn, y of tn. And the idea is, as we move along this, what we're doing is we're progressing along these parameterized partitions, basically, as we go up. And so each one of these little pieces is a change in the arc length, some k change in arc length. And where we'll talk about this spot right here, this point, is going to be the x coordinate evaluated at t k minus 1, and y t k minus 1 is this point that the partition starts at, and then the top of the partition is just going to be x of t sub k, y of t sub k. So that would be the top of the partition. Everyone see that? So you start here, you do a little change in the arc length, and then you get to this next point. And so what we do is just like when a Riemann sum, when we do a partition, before we just kept the partition on a straight line. And then we chose something inside of these partitions because the size of the partition, we're going to shoot that to 0. And so we just choose any point, doesn't matter, any point inside of this partition, and that's the one that we indicate with the star, right? So this is now our chosen x of t sub k. So in the kth partition and our arbitrary choice, in the kth partition, our choice right there. So that's how all the pieces come together. So this is how we extend this idea of integrating along a line that's been parameterized instead of restricting to an axis. So going just against dx or just against dy. Just as a note, that the way we see the partition is that A is equal to the initial t value. So A is the initial t value, which will be less than t1, which will be less than t2, and so on and so forth, which will be less than the very nth one in the partition, which is B, okay? So that's why I could have basically put x of B or and y of B there. Okay, and so if we now put a surface, so this is the input space, and if there's going to be a surface above this, some z, this is going to be a scalar value function. So z is equal to f of x, y. Then what happens is when I'm trying to do this summation along, think of, okay, who's here's been to either a play, you've seen like a live curtain that they pull onto the stage and all of that. I want you to think of a line integral as sort of doing like a curtain over a stage, where if you're looking at a top down, so if you're working you're working on the stage crew, then the path of the line from a top down in the xy plane would be like what the curtain thing that it's coming from is shaped like. So the thing that it's being draped down from the top, that is the shape it would make if you projected that looking down. And then the surface itself is the curtain. In other words, you are taking an area because that area is whatever is underneath your surface out here, specifically cut along this very specific path. That makes sense? You're kind of making these rivets underneath a surface instead of necessarily just integrating across. Okay, is that good? So we did double integrals. We took an actual region in R2 to get volume. We're not doing that right now. What we're doing is we're taking, here's a surface. I want to go a very specific path underneath the surface and see what area that ties me out, that ribbon of area. And so this Sn, that's what we're doing here, is we're summing up from all of the partitions, right? So k is equal to 1 to n of the function evaluated at each of these points, right? We want the chosen point inside of our partition. So f of x of tk star, y of tk star, and then times every single bit moved over in arc length times delta s to k. So that's going to be that sum that we then turn into the definition of the line integral. So from here, we're going to get our definition. It'll be suppose the scalar value function scalar value function f is defined on a region containing the smooth curve and then C, which is given by the vector value function R of t is x of t on y of t, that vector. Again, this is parameterized, so always indicate your parameterization bounds a to b. So then the line integral of f over c, the function, the surface, over the curve path, is, and so integral c of f of x of t and y being parameterized with t as well, differential of the s because it's arc length, and this will be the limit as the size of the partitions goes to 0 of the summation we just talked about. So k is equal to 1 to n f of x of tk star, y of tk star, delta s k. Provided this limit exists, and if this limit exists, then we consider it to be integrable, at least the function f to be integrable over the curve C. So this idea of now the limits of integration, the region basically over which we're integrating, is described as some parameterized curve in the input space. So here's the journey of thought. Calc 1. We're taking an integral where the interval is some closed set of real numbers along x. And we do that underneath a curve to get an area in the plane. Okay, so now we step that up. We say in Calc 2, what about we do a double integral? So that double integral to get the volume is basically going to say, I have a surface out here, and then I'm going to, my region of integration, basically a bounds of integration is restricted. I'm going to close some sort of a region here. That'll be what I integrate. I get a volume. Triple integral is kind of the same thing. And so here, I want you to think of this curve R as basically just being now an advanced idea of the regular integrals or of like a double integral, but more selective. So instead of just taking a whole region, like I could have just put this in an entire rectangle to get a volume, I'm instead specifically slicing out, I only am interested in integrating underneath the function values that happen to be on top of whatever this parameterized curve is. Okay, so don't see this curve as the function in itself. Okay, see this curve C, see all that the discussion about C is going to be oriented around how we talk about describing a region that you integrate over. That's the parallel. Make sense? Okay, because the biggest mistake I made when I first learned this was I thought that we were talking about C. So then I was confused. I was like, well, hold on a second. Isn't this the function? No, this is not the function that we're integrating. The function that we're integrating under is the surface. This is describing where in the input space we're integrating. That's the difference. Okay. All right. So questions before.
So where is the function figure?
It would be out here. So imagine this was a double integral problem, and I just drew a rectangular region. Here's the surface. So now you're integrating the whole volume. But now instead of taking that whole volume, we go, no, I just want this ribbon cut out underneath the.
well. In order
Mm.
to take it out into the, yeah.
The reason why we don't is because of the way that we constructed the sum. It's because this accommodates for the function value, so this is the z value, essentially. So this right here is accommodating that, the third dimension. This is telling you how tall it's going to be, essentially at that chosen point, and then multiplied by how much you've shifted over. So you're making these kind of strips of area that get added up.
So the integral of C is then the integral for that line.
Yes, as you
Not-
all of these.
Okay.
The textbook has really pretty pictures of this that I can't draw two-dimensionally, so I'd look at them. But this is, yeah, it's good. Questions? Yep. There are a few different notations you need to be familiar, so that if you see it in Pearson or something, it's not like confusing. That same idea can be written as integral C f of the vector r of t, ds. Can also be written as integral C f of x y ds, where it's implied that you understand x and y are parameters. And then this is how I would do it. Just because I'm lazy, but also because I know that f, all the nuances behind what each of those symbols are representing. Okay. So in case Pearson decides to throw random notations at you with no explanation, here you go. That's if they're all synonymous for the same idea. Okie dokie. Boom, 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 boom. So the length of C over A to T. This is nothing new. We're recalling this from Calc 1. Is A to T, or sorry, not from Calc 1. We're recalling this from earlier in this class. That's arc length. And so this tells us that S prime of t is equal to magnitude of r prime of t. And S prime of t is ds dt. So ds dt is equal to r prime t. The reason I do that is just so you can have a better visual understanding of ds is equal to that. So this relationship right here is very important.
In front of the G square bracket.
Is that A?
Is that A?
A to t. So constant A. Yeah. Okie dokie. So this is like a preliminary thing that you'll need for a future result. Okay. Let me know when you've got that. Yes, question.
Is there a reason why it's r prime u du and then it's switching to t?
Here's the variable of the function. We need a placeholder, so this is a dummy variable for the antiderivative. Then when you differentiate, the t drops into the function. Yes, it's easy to forget.
Why do we think S prime of T then from S to T?
Oh, we're differentiating. So we're starting with the arc length formula, and then we're finding a relationship between ds and dt so that we can get rid of this annoying ds thing for practical computation. Okay. So, any questions, or you get this down in your notes? You can give me a thumbs up when you've got this on your notes. And then, of course, these are all recorded, so it technically isn't. Like it's lost forever. Okay. Moving right along. That's the reason why we're able to have the formulas for computation. That the integral for FDS can be done in different ways depending on what's going to be easiest in context. So we could do f of and then x of t, y of t, and then r prime of t, because this right here is the ds, right? And that would be good. And so this is specifically in R2. And so the magnitude formula, if you just remember, we would have A, B, F, X of T, Y of T, and the square root of X prime of T squared plus Y prime of T squared. Because then this right here, if you remember the definition, is F. So don't forget your definitions, they're important. In general, if I wanted to generalize, so that's an R2. So generalize to Rn, I could say that this F ds is going to be given by integrals of A to B of F times that just by itself. Because then this vector could have as many parameters as I want, and the function would be parameterized to as many parameters that helps. Okay. That's just a side note. We should move into the next thing. Yeah, I'll get a fresh board for this, because now we're switching focus. So that is all, that has to do with evaluating scalar value, like line integrals for scalar value functions. The meat of the matter is going to be the vector stuff. Yeah.
What's above the R?
And
Oh, I forget.
so instead of, because this is R2, I leave it to you to just determine what this looks like for R3.
Mm.
Yeah, you just put Z on there. It's not rocket science. And then N, instead of writing it all out, you can just give it by F and then R prime T. Cool. Not as important, but I know Pearson will probably make you do this by hand, so you know what it is. All right. Thumbs up. Okay. Oh. You know what I should do? I should create a Pinterest board for all of the different props that I need to collect over time to teach every single calculus 3 section. And then just over the course of my life, collect them all and build them all and bring them into class until I get in trouble by somebody, I don't know.
Javier, you don't even write on the whiteboard. It's all props.
Props. Lego Calc 3 like okay. So here what we're gonna do is we're gonna shift over to the idea of fields. Okay, so how a line integral is going to interact with a field. I'm going to draw some sort of curve. This is designed to be in R3, but I'm not gonna do an axis because that's just gonna be more confusing than it needs to be. So here is, well, but I could, you know, let's see. If I use this, okay, let's do this. So wait, hold on a second. I sorely miscalculated that perspective angle. Okay, so I want to do something that's kind of like down, a little more over. And then if I have some sort of a curve that's moving through X, Y, and Z, like maybe. Boom. Beautiful. It's a peanut. Okay. And parameterized curves have orientation, right? Because as you trace them out, they're going to go in a specific direction. So there's, I'll give this an orientation. So we trace it out specifically like that. And you guys still remember what a unit tangent vector is, right? Yeah, it's a vector that's tangent to the curve, and it's the magnitude of one. So it's like right here, the unit tangent vector is like that. And notice that the unit tangent vector always points in the same direction as the orientation. So I would not have the unit tangent opposing the direction of the curve's orientation. That's what it means to be oriented, okay? That's it, well, that's a very, very layman's term way to describe what that is, but it's sufficient, okay? So P, again, so just every single point around here, I'm only drawing a few, for example, so you can get a visual for this. So why do we care about this T? Well, this is going to help us measure how aligned a curve is in the field that it is surrounded by. So if we now impose a field into this three-dimensional space, let's take a look at how it interacts. Now, I'm not going to define it something specific, I'm just going to draw examples. But like, for example, what if at this very exact point, the field is not going that direction, it's actually going this direction. Okay, so the actual field at that point is a vector going like that. Well, now there's in some angle theta between the tangent, I mean the unit tangent for the curve and the actual field, which you can kind of more physically think of as a force per se. And then maybe up here, it's actually opposing the direction. So the field itself is pointing in an opposite direction than the orientation of the curve. And then maybe this one's just straight up orthogonal. So we have some right angle maybe. Okay, but the idea is that these are all theta values. And then maybe what if it's perfectly lined up though? What if I like line up the field, boom, the field is also the same. Okay. So these are the different cases you can have. Acute angle between your unit tangent and the field, the opposing angles, right angle, perfectly aligned. Okay. Now, think of dot products, okay? So if we look at the component, the fourth component or the field component, F cosine theta, again, T is a unit tangent vector. The magnitude of a unit tangent vector is 1. So I'm not changing anything by then multiplying this by 1. Does that make sense? So I haven't changed anything because the magnitude of a vector whose magnitude is 1 is just 1. So this times 1 is this. And then, do you recognize this definition from all the way at the beginning of class? F dot T. You're going to see that so many times, you're going to be vomit sick with it by the time we're done with this chapter. Okay. So, if you have some sort of a vector field, I don't want to write this out, so I'm gonna abbreviate the important parts. So we're gonna have F is a vector field. Okay. That's going to be continuous. On a region that contains, so containing C, which will be a smooth oriented parameterized, smooth oriented, and then parameterized by our claim. Okay. T is the unit tangent vector. Okay, so T is unit tangent vector. And if you have those ingredients, now what we got is if we're now going to integrate over the curve C of the field and the unit tangent vector of ds. Okay, so what is this really saying? Well, it's summing up every single dot product between T and F all the way around, and it's going to get the total number of contributions. Okay, so here, is this contributing positively, negatively, or 0 to the overall integral? Yeah, why?
Because they're roughly aligned.
Yeah, they're more aligned. In other words, the angle between this is less than 90 degrees. So the dot product will spit out a positive number. What about this though? Yeah, And that should make sense. That's why I want you to think intuitively of work. So if you're trying to push some sort of object through a force field, and the force field is going like this, and you're trying to push it this direction, okay, I mean, more or less, it's aligned. Way easier than that, right? If the force is pushing you this direction and you're trying to get through around the curve like that, that's going to be taking away its negative work. And then here, when it's exactly 90 degrees, what's cosine of 90 degrees?
0.
Okay, so is the field in any sense contributing at all?
No.
No, so no work is done. So then that would just be 0 at that instant. Here, we're back to perfectly aligned, but perfectly aligned maximizes the dot product. Because if cosine of 0 is 1, then we're just taking exactly the product of the magnitude of the field, the force pushing you in that point, and the direction you're supposed to be going. It's perfect alignment. And so this integral is a description of every single infinite number of instances of dot products as you go around, evaluating what's the relationship of the field that my curve is surrounded by and the direction that my curve is trying to go. Okay, so when you're in Saga, after chapter, if you're trying to take this curve, how efficient is that? Well, it's doing pretty good until you hit here. Okay, and then you got a bunch of people pushing you this way, you're trying to get through to the bathroom or whatever, okay? So the idea is, if you were to look at a top down of Saga the traffic flows, they use fields. And then the streamlines, and so you want to be as parallel as possible with the streamlines to maximize your efficiency, because then you want to make this integral bigger. That is, you have less counteracting against the field, and then you'll expend less energy.
So the integral and the final integral would be like average TR.
I would say average. I would say this is the summation of the total amount of work done basically by the field on the curve. Yeah. This is actually how we eventually define work. It doesn't look like it yet, but this is pretty much how we define work using line integrals and fields. Making good time. Okay, good. Any questions about that? So if you understand that, that's the hardest part about this, okay? Is you gotta know what's happening. Because when you start seeing weird combinations of alphabet vomit like this in your problems, that's terrifying. Okay, you need to know what really is being described. It's not that complicated. So what's happening isn't that complicated, but the way we have to handwrite it out can sometimes look just totally foreign to the concept. So here's the anatomy of how you see something like this. C. Okay, so there's a curve. It exists in space. Fantastic. Okay. Field. Okay, so in that same space that my curve is inhabiting, we've imposed some sort of a field. Think of it as a force or something so that you can kind of hold on to it. T, okay, that's just telling me the direction that the curve was trying to go at every single instance. And so this dot product is a measure of parallelness. Okay, in other words, how aligned is the field with my curve? More aligned? Yeah, really not aligned. Neutral, right? It's 0 amount of alignment and then perfect alignment. Okay, so there's gonna have all these different kinds of things going on. When do I stop? Well, I need to do all of these dot products along the entire arc length. That's what the DS is going to stand for. All of the bits of arc length. As you go all the way up. Okay. And so that is Mr. F.PDS. We're going to see a lot of him, and you'll need to understand not just that notation, but the idea that it's trying to describe. Because Green's theorem, and as we go forward with like curl and stuff and divergence, is essentially going to be taking this idea, but then talking about it in higher dimensions. Okay, so this is like the one-dimensional version of that. All right. Thumbs up if you got that. Cool. Great. I was practicing drawing some of the figures for this lecture, and I could not for the life of me get the axis to not make the curve look like it was like pizza being swung in the air. Which is interesting now because I have an Italian brother-in-law, so that's a lot of fun. Okay. This is like the second part of the business. Okay, so the unit tangent vector as a means of this definition is this, right? If you take a vector and you divide that vector by the magnitude of itself, you get a unit vector, right? It'll have a magnitude of 1. Okay, and then obviously, so this will be put together in conjunction with the other thing that we did, where we were calling that BS is equal to, right, so. You'll need to show this. So like, you'll show this part first. And then you won't need to recall it because it'll just be already there, and then you drop this definition. And then now we're going to, right now we have the integral in terms of arc length. Arc length is a horribly not practical way to do computations, so we're gonna move it over to the parameter t. The way we can do that is this is the main player. So we start with our good old f dot t, right? So f dot t ds. This is describing, again, when you see this, I want you to think, okay, I've got a curve. The curve is in space. Guess what's also in that space? A field. Okay, the curve is interacting with the field. We want specifically this relationship, the dot product relationship. I'm like, how aligned is my curve with the field? And then do that for the entire curve across the earth. Okay, that's how I need you to read that. That's how I need you to see that. Then this will make so much more sense if you understand that. We're going from A to E, F dot, and then the T is R prime of T over the magnitude of R prime of T times magnitude of R prime of T dt. So this right here is your T. This right here is your ds. Ooh. Okay, and so now when you simplify, you get integral from A to B, the field F dot just the R prime. Because you cancel the magnitudes of R prime. And it's hanging out. Now, just so you know, recall basically that the R dt is the way we write R prime, right? So really, if I'm to kick this over, and if I have dr is equal to R prime of T dt, I can actually replace this with the differential dr. Okay, so I have, and you'll see this a lot in higher textbooks, especially in EMAG and other things like that, circuits, or magnetism. And so you get F dot dr, so over the curve F dot. So notice that here, I switch back to using just the C. Here is A to B because I've literally explicitly put this to the parameter T, but now I'm just talking about my curve again over the dr. So make that change. Do not put A to B, F dot dr, it's wrong. You got to get back to your curve when you're talking about it. Okay. So know how to do this. Know how to put that together, including the construction of this. Okay.
How would you solve that last part out of, oh, do you?
Yeah, this is nice because when you're given like if you're given a field and you're given a curve, the problem will be like, oh, field is equal to blah. Your curve parameterized by R is equal to blah. Well, then you can find the dr simply by just doing that. Yeah. So you need to know all of it. That's the thing. All of the pieces matter because otherwise, when it comes to being given a certain circumstance, you just won't know how to compute it unless you know the relationship between all the pieces. Because each context will be slightly different depending on the problem that you're given.
However, the dot still has to be present. Well,
Yeah, I mean, it's a dot product. That's not changing about this. It's still a measure of alignment. How aligned is the field with the curve? Good questions. Anything else on our lovely happy guy? Thumbs up? Cool.
It's probably use Jacobian to get to magnitude of R prime T. Cause it looks like we're just changing read.
I want to say that it probably does work. The only thing that I'd be maybe concerned about is Jacobian's more interested in scalar valued functions relating to scalar valued functions. In other words, they're spaces to spaces. This is saying re-represent a parameter to basically instead of talking about the parameter in its one spatial dimension, talking about the instances at which it is at its particular. So it's probably, I mean, there's probably something, I just can't think of it right now. Look it up, extra credit vote. If you turn in that instead of a lab, I'll just give you full credit. Speaking of labs, I did push back the lab that's due to Sunday, but that means you're gonna do it as if it's due today. But then just so that I don't have to fix all the late blah blah blah, I'm like, I don't care, just put it back. So also, again, guys, it's November, guess what? So the time that you had to catch up on Pearson is only now 4 weeks. Okay, so if you're behind on Pearson, please, for my sake, because I'm trying to think, it's a game of politics. Okay, I'm trying to come to Dr. Hart and say, hey, this person should get an A in the class. But if you've done half the homework in the entire class, that makes that a really hard sell. Okay, so I'm trying to basically feel like a lawyer. It's like, hey, my client has done really well on their exams and they've turned in these number of labs, and sure, maybe they get like totally slacked out on the homework, but like they're a good kid, you know? That's a little harder to do than if you do 90% of the homework and perform on the exams and like, boom, not even a question. Let's give him an A and move on. Okay? Because Calc 3 is a 4 credit hour class. You don't want, I'm just saying, okay? So please, please, please make it easier for me to petition on your behalf. Okay. Turn in the Pearson. And because I'm forgiving if it's late, I mean, just do it. Even if you have to just click on show example to the point that it cycles to the same problem, you just put the number. I don't care. I don't care anymore. Okay. Because if we're being honest, Pearson's gross enough that that's probably less sinful than doing the Pearson problem itself. Okay, so but you hear me though, please do it. Okay, it makes it really hard for me to argue for things like, you know, extensions and stuff if there's like a 50% turnout rate. Okay, so do it for yourself as a class, but also for your own personal grade, because I mean, if someone's got like a B in the class, but their exam stuff is really fantastic and their lab stuff, they turn all those in. Sure, okay, maybe your homework is great, but at least a B, you know, something, okay, so that it can be excused. Okay. If it was my choice, this class wouldn't have Pearson homework. The lab would be the homework. See, but then I still wouldn't grade homework. Just put 100 on it. I figure if you can do these exams, then you know Calc 3. You know, so okay. I'd like to see. Honestly, I would like to see people who have formally taken this class take your guys' exams and see what they score on it. Because I don't know, man. H. Okay, so here's a field. Again, F, G, and H are scalar valued functions. So these are actually just like, no, depending on your point X, Y, Z, you'll spit out a number, but it's a vector. And then we got a curve that has been parameterized, some R, that's also existing inside the space. X of T, Y of T, Z of T, right? Parameterized data dimensions. Because it's parameterized, we need to specify it in equal. Okay. So there are 3 computational algorithms, choices that you have to handle these kinds of things. So if you decide to go integral A to B, f dot r prime of t dt, what you could do is you could just do A to B and then, you know, blast out the dot product, right? Because f with the x's, g's with the y's, h and the z. So you could do in the integrand, you could have f of t times x prime of t. Notice that's prime because this is r prime of t. So don't just plug in the x by itself, it needs to be differentiated. X prime of t plus g of t y prime what? Plus h of t z prime of t. So you could compute what all those are given your stuff, and then just slam it into the integrand, make sure everything is in terms of the variable t, and then bada bing, bada boom, that's okay. It becomes a Calc 1 problem. Another way you can choose to see it, of course, is just C of, this will become somewhat relevant later on as F dx, G dy, and H dz. That's just an expansion of the dot product there. And then, of course, the most famous, the lovely F dot dr. This is stamped into my memory every single time I hear in my name, I think of F dot dr. Your work integral, your circulation. Flux. Chapter 17 lore goes crazy. Because there's gonna be two rising heroes. It's gonna be flux versus divergence. And they're gonna do opposing things. And then they have an interesting relationship. Or I could just touch grass and do more than doing mathematical homework. But hey, you know. Okay, so this is how we define works. So the circulation integral is the work integral in physical application. This is also the F dot T. Let me see. I got the, okay, yes. So let's talk about the difference between circulation and divergence, because what's going to happen on Monday is I'm going to introduce the evil twin sister. Okay, so we've got F dot T, and we're going to introduce a different one. It's basically going to be summing up, and so the idea is the same. So you're summing up contributions of the field, but how the field contributes is what's going to change. And so it's going to be the way we interact with curves being inside of things that have fields going on. So let me erase this. Chapter 17, honestly, it's a really fun chapter. It's high volume, but it's a really fun chapter. I think part of the reason. The what?
Why did they make it chapter 17?
Because it's the culmination of Calc 1 through 3. You have to know all of that language to interact with this stuff. And the crazy thing is, you know how in Calc 1 they'll say, well, the proof of this result is slightly too like it contained an advanced text. I am in those advanced texts. This is hard enough that the advanced texts for these are the advanced texts that are referenced in my advanced text that were called the advanced text in Calc 1. Okay, so you go to grad school, you get master's degrees to be able to prove some of these results. So we're really enjoying the fruit of the labor of pure mathematicians in the field of vector calculus, so to speak. So vectors go so much further than what you think a vector is. I'm not going to spoil that for you because when I lost my innocence on that, I'll never get that back. So yeah, they're pretty arrows. Everyone eat their cake. Okay, so let FB continue with vector. Actually, you know what? I'm going to make an executive decision against myself to not write this because there's a better way I can teach this to you. Okay. So I'm going to split the board in half and we're going to compare. You need to see this before the weekend because I believe in the power of sleep and math marination, where you'll have seen it and then it'll like hook. And then you'll come on Monday and be like, oh, 2 months. Okay. So over here. Okay, guys, bring it in. This is important. This is going to be the contrast that is going to be made for the rest of the class. The rest of the chapter is all about the relationship between these two ideas. Okay, so here is what we already talked about. So here I get some sort of a curve that's going on in 3 dimensions. Okay, so it can be parameterized 3-dimensionally. It's got some orientation. So I want it to specifically be oriented, drawn that. Now, what we talked about was this idea of circulation, as in how is the field aligned with my unit tangent. So if this is my unit tangent, and I'll just draw several of these as an example and make sure we really get this idea. All right. Okay, so like, if I was trying to get the most possible amount of alignment, like circulation around this curve, how should the field behave close to basically my tangents, close to the curve? Should it be more aligned? Should it be more orthogonal? Should it be opposing? It'd be more aligned, right? So I wouldn't want to do something like this, right? Because that would oppose. So what I want to do is have more alignment, right? So that's really good. Narrow theta, another really narrow theta. Okay, there's another. I'll just make this one perfectly aligned. Parallel, narrow theta. Okay, so this, we're collecting a lot of circulation. This curve is really efficient through this field. It's moving along the streamlines almost perfectly. This is going to produce a lot of work. This is the idea of circulation, which we're going to call flux. Okay, so the abstracted idea of this is flux. I put it in quotes because technically, well, we'll get there next week, but now there's the evil twin. Best part about this is I haven't referenced the textbook on this in a year, which means if I say something objectively false, that probability is non-zero right now. So I will definitely rectify any incorrect things I say if I catch it. Yeah. But so now say we have a curve. Again, so we have a curve. And then we need it to be oriented. Now, okay, let me put it this way. If I am trying to, say below, you ever seen those really massive like bags that's just like you have an opening, or like a trash bag or something, and it's got this. So if you want to blow a puff of air in order to try to make it expand as much as possible, at what angle are you going to blow air into the trash bag, right? Well, you'll open it up and you'll preferably hit it as orthogonally as possible, because then it's going to push as much. In other words, you're maximizing. You don't know what it's called yet. That's just called divergence. In other words, how orthogonal you are to the curve. You're putting in a force that is going orthogonal. Now, this is all about alignment. Divergence is going to be all about orthogonality. How much field is now intersecting, passing through, crossing out of your curve instead of being aligned with your curve? You'll curl around. That's why it's called curl. Flux, but divergence is going to be poking through. You're trying to see how much of the field is essentially opposing the direction of your curve. You can think about it as, so let me draw. And so instead of doing the unit tangent vector, we have something called a unit normal vector, you know? And instead of being tangent, it will be normal. Wow, you guys are already math majors, eh? So, boom. Normal. Boom. Normal. We're going to ignore that these are all blatantly different magnitudes when they're supposed to all be magnitude 1. Okay, so these are the normal. So if I'm going to copy over as similarly as I can the angles that I did here, so you can see the contrast, okay? So over here, I have the field kind of going like this. Here I had the field kind of going like this. Here I have the field kind of coming off of this. And then down here I had it coming down. Okay, well now there's a difference. Suddenly these angles are bigger. Okay, so the field is not very aligned with how normal it is. Are we surprised by that? No, because we literally designed the field to basically be aligned with the curve itself. So I would be concerned if it being aligned with the unit tangent, we're suddenly also aligned with the normal. That's what we're talking to it, okay? So we are less aligned, which means that the contributions essentially of each of the field, the field component coming out of the curve or crossing through the curve is less. How would I increase the size of the dot product between the field F and the vector n, the normal vector n?
Increase the dot product, you can call it reduce the angle.
Yes, reduce the angle, essentially do what we did here. The closer, the more aligned I can make the field with whatever vector I'm talking about, that's gonna make the overall dot product bigger. Okay, when's it maximized? When is this dot product gonna be maximized?
Theta 0.
Yeah, theta 0, so it'd be perfectly aligned. So this is going to be what we consider to be divergence. And it's gonna be this measure of how much is passing through the curve. So that is what the rest of the entire chapter is about. It says, here's flux, F dot T. I'm sure it's probably no surprise that when we do the divergence. Oh, I just trolled myself. This is flux, this is curl. Curl. Right, because it's going around. This one is nice. Now the internet can know that I got those confused. Okay. So curl this. I'm so sorry, Chloe. Did I mess up your perfect note? I know. I'm kind of disappointed in myself at home too. Okay. All right. So here we got see F dot. What do we can put there? And I don't think he calls it capital N in the book, but because it looks pretty, I'll do it. And then D over the arc. So you can imagine on Monday, we're going to break down what NDS is supposed to become, right? When we parameterize that. So today got us from the F dot T. So here we were doing F dot T ds. This idea we were able to construct from what we were trying to do to the notation, which we were then able to show for practical sake, is the F dot dr. Okay, that's what we got. Now on Monday, we're going to talk about how to get this basically the other way, flux, measure of the normal instead of measure of alignment with tangent. How do we get NDS to be parameterized? Okay, so the rest of the chapter tells a very, very fun story. And when we get to the section called divergence and curl, it's basically going to be divergence is going to relate to flux, curl is going to relate to curl. I think I'm supposed to put the word circulation here, so I'll just throw it on here so you have it, circulation. And then divergence will be over there. But yeah, this is going to be extended into 2 dimensions for Green's theorem. When we extend it into 3 dimensions, we split ways. Mr. Curl is going to come over here into 3 triple integrals and become Stokes' theorem. Flux, or I'm sorry, that one's technically stayed as a double, but we'll talk about why there's a nuance by that. But then flux is going to come over here. And then in 3 dimensions over a triple integral, it's divergent. So this is why this is so crucial, because the rest of all of the sections are just elaborating individually on these 2 ideas. Yeah. Okie dokie, that's good. And on time-ish. All right, I will see you guys on Monday. Please actually, well, if you're going to prioritize, do Pearson, but read up if you can. All right.